For the longest time, engineering was all about experience, intuition, and, well, making things a little bigger than they needed to be just in case. But a revolution is happening right now. We're watching engineering transform from an art of guesswork into a science of certainty, and it's all being powered by data.
So let me ask you this. What if a factory could fix a problem before it even happens? I mean, really think about that. Imagine knowing a critical machine was going to break down days or maybe even weeks ahead of time. This isn't some sci-fi fantasy anymore. This is the new reality of engineering.
What we're really seeing is a fundamental shift in philosophy, a totally new way of thinking. We're leaving the old way behind, waiting for something to fail and then scrambling to fix it. Now, we're in a whole new era. We're using data-driven insights to predict and prevent problems. We're operating on certainty, not just assumptions.
So how in the world do engineers pull this off? Well, it all comes down to a really powerful framework, the 4 pillars of analytics. The best way to think about it is like a ladder. With each step you climb, you get a more powerful, a more complete understanding of what's going on.
It starts with the absolute basics, descriptive analytics, which just tells us what happened. From there, we climb to diagnostic, which tells us why it happened. Then things get really interesting with predictive, which uses that knowledge to tell us what's going to happen next. And finally, at the very top, you've got prescriptive, telling us exactly what we should do about it. See how each one builds on the last?
So let's start at the bottom, our foundation, descriptive analytics. This is all about looking in the rearview mirror. It's kind of like a business checking its quarterly sales reports. By summarizing all that historical data, engineers can spot trends and get a really clear picture of how a system's been performing.
It's all about answering one simple but absolutely critical question. What happened?
Okay, next up, diagnostic analytics basically puts on its detective hat. It takes the what we just learned and starts digging deeper to find the real root cause of the problem. The whole goal here is to answer that crucial next question. Why did this happen? Now this is where things get really cool. Predictive analytics is all about turning that rearview mirror into a crystal ball. It sifts through all the past data, finds those hidden patterns, and starts to forecast what's just around the corner. This is a huge leap, right? It shifts us from being reactive to being proactive. It forces us to ask, what happens next? And finally, we get to the top of the ladder, prescriptive analytics. This pillar is the ultimate payoff. It takes everything we've learned, the what, the why, and the what's next, and it gives you concrete, data-backed recommendations on the absolute best thing to do. It's designed to answer the ultimate question, what is the next step? This is where data turns directly into action. Okay, so that's the theory. Let's pull this down to earth and look at one of the most powerful, real-world applications of this entire toolkit, predicting machine failures right there on the factory floor. And believe me, the stakes here are absolutely massive. When a key piece of equipment goes down without warning, it's a total disaster. We're talking lost production, huge amounts of wasted money, and seriously unhappy customers. It's a gigantic problem industries have been fighting for decades.
The solution is something called predictive maintenance analytics. What it does is brilliant. It combines a constant, real-time stream of data coming off the machines with super smart machine learning algorithms. This combo constantly evaluates the equipment's health and, this is the key part, predicts its future performance.
So how does this magic actually work? Well, you've got these tiny little sensors and meters, part of the industrial Internet of Things, that are always monitoring things like temperature, sound, and vibration. All that data gets streamed to the cloud, where machine learning algorithms are just crunching away looking for those tiny, subtle patterns that are the very first warning signs of a failure.
I mean, the difference this makes is it's night and day. The old way, reactive maintenance, is all about fixing a machine after it's already broken. Predictive maintenance is about scheduling a repair before it ever even has a chance to fail. It's a complete game changer for any factory's efficiency and reliability. But what happens when a single prediction just isn't enough? Because let's be honest, the real world is messy, it's random, it's variable. So the next big frontier for engineers isn't just predicting one outcome. It's about understanding the entire spectrum of what could happen. This is a really cool concept called Uncertainty Quantification, or UQ for short. Let me break it down like this.
Instead of designing a bridge to hold one single specific weight, UQ helps engineers understand the whole range of possible weights it might see, and the whole range of possible strengths the materials might have. It embraces all that real-world randomness by looking at probabilities, not just single fixed numbers.
Now take a look at this graph, because it shows the power of UQ perfectly. See those single vertical lines? That's the old way of thinking. The load looks like it's safely below the strength. No problem, right? But the curves show the reality. They show the probability. And that little overlapping area in the middle, that's the hidden risk of failure that UQ uncovers. It's a risk you would have completely missed otherwise.
And UQ isn't just about finding risks, it also makes engineering way more efficient. This here is called a global sensitivity analysis. It basically tells engineers which variables have the biggest impact on the final outcome. You can see right here that one parameter, x1, is responsible for over 70% of the variation. That tells an engineering team exactly where to focus their time and money to make the biggest possible improvement.
So you've got these incredible tools, right? Advanced analytics, uncertainty quantification, but how do engineers actually put them to work in a smart, systematic way? Well, they use a process, a framework, to get them from a complex problem to a real, data-driven solution.
One of the go-to playbooks for this is root cause analysis. It's like a logical recipe for problem solving with data. You start by clearly defining the problem. Then you go out and collect all the relevant data. Next, you brainstorm all the possible causes, use the data to pinpoint the true root cause, and finally, you implement a fix. It's a structured approach that makes sure you're solving the right problem. So, all of this brings us to one last, pretty mind-bending thought. We've gone from just reacting to failures, to predicting them, and even to quantifying uncertainty itself. So, what's next? As this data revolution keeps accelerating, are we going to see a future where machines learn not only to predict their own failures, but to optimize, to adapt, and maybe even to repair themselves all on their own?